Okay, before we walk into more deep into the synthetic discussions, we have to touch upon some of the practical side of the organic chemistry. So we've been talking a lot of mechanistic study, and that can be supported by computational theoretical work as well. However, if we don't based on these theoretical thinking, it's no different from the philosophical ideas. The previous videos are structured like covering some aspect of potential energy that governs every structural or property changes. Then we move on to the structures and why molecule takes up a certain geometry, or due to the geometry, what angle does the certain chemical bond has, and based on that structure you can deduce the property of certain compound. So we had some videos covering first potential energy, then about 10 videos on structures, how to deduce structure in the head and how to draw them, to visualize, at least to help us to think with, and then the acidity or nucleophilicity and what type of reaction or mechanism that chemical mixtures actually taking that was possible. However, again, that's just activity in mind. In order to connect that with the physical world, the realistic world, we need to be able to observe and measure and apply it to the physical setting in order to predict or create something that's predicted by thinkings. So in thinking process, we looked at how the electromagnetic force, one of the four forces in the universe, controlling all of these structural features. Then based on the structure, we went on to predict the physical and the chemical properties. That's what we did in our previous theoretical lessons. But now we need to base on the measurable properties. Thus we can measure some of the properties, and based on that we can deduce the structure and we can deduce their energy. So we can connect with our theoretical work the formulas and every single thing we know about the chemicals, connecting all in the potential energy, so we can freely use the concept back and forth in order to think theoretically this way, and also plan for doing something in the experiment, so we can come back and make up a more complete set of the rules, so we can get help from it to do better job on applying to the real world. So what can we measure? Yeah, we can measure melting point, boiling point, and solubility, and concentrations, and reaction rate, etc. But they are all essentially based upon electromagnetic force. So using the electromagnetic force, all the mechanisms, the design of synthesis, we can prove it. So we can say make a new drug to cure certain disease or make a new material for astronauts, etc. So let's be practical. We need to measure something. Spectroscopy. Yes, spectroscopy is one of the main tools the organic chemists use to measure the properties that's coming from the sample or reactions. Yes, spectroscopy uses electromagnetic forces just like our vision. If there's an object in the presence of light, we can see the object. At least that's what we think, right? The light is oscillating, fluctuating electromagnetic force that's gonna be working on the object and causing some change inside, and also in reaction, light will get changed. Then it'll reach our eye, and eye will be able to pick up a certain information of the light, and our sensation and brain is specialized in constructing that type of information, electromagnetic force, into a certain form of idea. So if the object was an apple, for example, you don't really see apple, right? There's no such thing as apple element. The apple consists of many chemicals, and with our eyes we only get small portion of the properties of the skin of apple. And if you zoom into the skin, you have a lot of carbon compounds that emits certain color wavelength. So what we actually detect is light coming out of the electron motion in the carbon compound, and then that pigment is occupying a certain space, but the pigment is almost empty space with the electrons moving around the nuclei. So the light carries a certain strength and energies of electromagnetic field, and that light electromagnetic field pass by the object. Then the electron is disturbed, and because of that, the light is also disturbed, and then the light, the original light, after alternated, is coming to us, so we are capturing that light. Then the brain is making up a certain thing for us to survive and get information. So the instrument that's used and made for spectroscopy is a more sophisticated system in a way, not necessarily, but in a way, for observing certain properties, sometimes out of reach of our human ability, such as this. So the computer is there to pick up the electric signal from the detector, which correspond to our eye. The computer probably is corresponding to the brain. Then the object that we are putting in the machine in the spectroscopy technique is normally relatively pure compound, and you don't see it because most of the time it is in the solution form or gas form, sometimes a solid form, so you can see them. And then the kind of light you are giving, you will learn as we go on, but you have to choose what type of light you are using to detect what type of property that you are trying to detect. In doing so, there is one barrier. The structure that we are trying to detect is too small in our case. And as I described a little bit earlier, the property that you are detecting is not direct observation of the motion. You are observing the electromagnetic force that's present inside of the photon, and you have to deduce the properties of structure indirectly. For that, you need physical and chemical theoretical background. So let's make up an analogy. The barrier we have for our sample will be size. But to connect our concept of physics better, let's introduce a barrier of a box while you are trying to observe how frequently this little magnet hung on the string or it could be glass rod you rub with a silk to polarize them this manner, or you can think of something vibrating constantly with a plus minus sign, and you can also imagine that as a spinning at the same time as it vibrates. So if those properties keep spinning or vibrating, you can use a detector for the magnetic object. You can use compass probably. So as it turns, the compass will turn. And if you observe it carefully and say you can feel it, the rotation is giving you the end pole of the magnet getting closer and closer to the detector. So if you look over here, the strength of the end pole magnetic field, the strength gets greater and greater, and as the end pole turn away and walk away from the detector, then the strength becomes weaker and weaker. But soon the S pole is gonna come around and get closer to the detector. Then the end pole of the detector will point to the box. So it's gonna get more intense and more intense S pole. And then as S pass away, it gets weaker and weaker. Then the N come around, and that's gonna be the wave of the rotation of the magnet, and at the same time that will be the wave of the detector. However, I don't think there is still a good detector that can detect the movement of single molecule or electron in the molecule. Basically, the object you are trying to measure for our chemist perspective, the force, the electromagnetic force coming out of the sample is too weak to be detected. So we need a different idea. So if we can give this oscillating strong wave input, for this case we can create strong NS kind of oscillating wave by spinning bit big magnet maybe, and then let this wave pass through the sample, and then have the detector detect the input after passing through the sample, hoping certain motion that sample had is disturbing the input. So in summary, I can say the spectroscopy is basically detecting the stimulating electromagnetic light that was given with the control of us to the sample, and then sample interact with the input photon. Then whatever is given out, we are analyzing it and see the changes from the original input in order to detect the properties that's going on inside. And it is all the cases, they are motions, particular motions. In the chemicals, there are various motions that's periodically happening, and we can express them in a way using sine, cosine functions. And as the say magnetic or electric field oscillate coming from here to back to the original, we call the time that took to do that period. Or we can express the wave using the term frequency, saying how many times you get original spot in a given second. We call it frequency. So a certain motion in the chemical, if it takes less period, it means it's coming back to the original motion, original place in a shorter time. Meaning it's gonna do that, repeat that more and more in a given time, so it has a higher frequency. So smaller period is proportional to the more frequency. So when we give input light, electromagnetic force we are putting in, then the sample, its original frequency, is going to influence the frequency of the input. Thus, after interference, you expect something has changed on input, and the output photon will have a different information there. Because the frequency of the photon is usually very big number, it is more convenient for us to use wavelength instead of the frequency. For example, visible light has wavelength of 400 nanometer to 700 nanometer. Then you should know some of the periodic motion that repeats, they can be easily expressed, especially for those periodic motions out of the chemicals. They are harmonic motions because they can be expressed in sine, cosine functions. Some of those motions of the molecules are oscillations and rotations. So I'm gonna show you with the chemical structures what we can measure, such as a bond angle oscillation, which is vibration, or what we can measure of the molecular rotations, the whole molecules rotating, or electron that's rotating around nuclei, or the rotation of the nuclei. So those are the measurable properties, not directly, but using input that we control, and we get the output that we can measure strong enough, and we can compare the two, so we can deduce what type of wave motion was there, what harmonic motion was there, so we can deduce out using our mathematical skill. Then that somehow will be connected to the structural information. I urge you to go back to your general physics to review on some of the topics we deal with here, such as electric force, magnetic force, magnetism, rotation motions, or oscillation motions, and a lot of things like that. So when you have positive ion, such as a proton, near the negative ion, such as electron, the physicist defines the electric field is going from the positive to the negative. So positive is going toward the negative around. So you have this field, the area where you feel the force if you are charged the particle. And the opposite direction of the electrical field, you see the vector form of the electric field, not just the intensity scalar amount. So this could be confusing for organic chemists, right? Because protons are heavy and they're not moving. It's normally electron that's moving like at high speed, so they are more easy to move around. But this arrow is not motion of the particle itself. This is the direction of the electric field. But when we draw mechanism, we show arrow, and that's actually motion of the electron, like this way, and eventually going to the positive charge. That's the reaction arrow for organic chemists, telling the negative charge is actually moving physically. So reaction arrow is different from the electric field arrow. But anyway, if you are charged the particle and put it in the certain electric field, the force you get is a simple multiplication. And in the Coulomb's law, you can calculate, if you know the exact amount of the charge in Coulomb and the distance, with the sum constant multiplied and divided. Then in a given electric field around the charge, if you're trying to move with the unit of charge, you need this much of the voltage, which is basically potential energy, how much energy it takes. So distance between the two charges. So for chemists, this is a more familiar situation. You have protons in the nuclei, and you have a first shell and second shell, and those electrons, they feel force stronger than the one that's away from it. So these forces are a centrifugal force from the rotation speed, right? The reason the electron is not attracted to the positive charge and get very close is because of the centrifugal force. I didn't show the charge force because I have to draw long line passing the nuclei, to show the bigger size of the arrow has a bigger force compared to this, and it wouldn't make sense. So instead I show the centrifugal force that's opposite direction but same intensity, same amount of the electric attraction. So here you have a less electric attraction because they are further apart. So these are the pictures we are more used to. Now, what are the harmonic functions and motions you find in atom? First, you have nuclei actually spinning. We are able to detect that motion, and that's called the NMR. Okay, we detect the spinning motion of the nuclei. And the spinning motion of the electron in an orbital and the shell, not just the shell, more specifically s orbital, p, x, p, y, p, z orbital, or d orbital, those things even you can deduce with a more mathematical, sophisticated mathematical manipulation using UV. Then I hope you remember I said that you need to choose the right kind of input light source to detect a certain type of a motion. So in order to detect the nuclei motion, you need radio wave. And in order to detect the electron motion, we use UV, ultraviolet. Then there is IR. We use infrared to detect vibrations. Here, the vibration is taking place. You can think of two mass units attracting each other. In physical setting, macro scale, you can think of a spring, but in chemical, you have two mass, chlorine, carbon, connected by a bond. A bond is acting like a spring because the negatively charged electron is attracting either side of bodies. So you see potential vibration there, vibration here, there, 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 and there. And you can see every single vibration, you have a different mass or different strength of bond. So if you're a little person here with the detector, the oscillation from this vibrating bond, you can feel the plus charge is decreasing as it moves away from you, and start increasing, decreasing, and so on. So you see some sort of wave, intrinsic, unique frequency you can imagine for this. That's different from the frequency that you have over here, because they are consist of different mass unit, and the bond strength due to the proton number inside causing different electronegativity. They have a unique vibration out of this as well, and same for all of them. Therefore, again, I can say you need to choose right source of input light. So I said NMR uses radio wave, but radio wave is not just one single frequency light, right? There are a range of radio waves. And the nuclei of more than 100 atoms on the periodic table, they all have different mass unit. So their rotation frequency is unique for each atom. Therefore, you need to find exactly which wavelength or frequency of radio wave you're going to use for a particular atom. Not only that, same hydrogen you have, but you may need a slightly different wavelength to be able to detect different hydrogen nuclei. And that's due to the electron density around the hydrogen, but we'll get to that later in more detail. Also, for IR, we said we are using infrared light to check the vibration, because infrared, their frequency is much greater than nuclei radio wave frequency. They can specifically detect vibrational frequency. So those frequency. In comparison to that, radio frequency, meaning the nuclei's spinning frequency, is so much slower and bigger. I mean, frequency is less, wavelength is longer, and the period is much greater. And for electron here, they're not just there, and I mentioned it many times. The probability of finding the electron there is greater due to the low potential energy here, but the electrons are actually all over the place on the shell of the chlorine and shell of the carbon. Not only that, depends on the potential energy distribution, it could end up being found over here, or even there, and even here. Which means if we find the electron distribution, we know what potential energies is measured for certain orbital to have that type of electron distribution. Obviously, the electron in the pi and the sigma, or that sigma, or lone pair here or there, they all should have at a different energy level. Therefore, they all should have a different frequency. So we need to use different frequency of ultraviolet, smaller than 200 nanometer, sometimes greater than 200 nanometer, if we can make the electron quite unstable. So this should give you idea, like chemicals is not just symbol and the line, but they are collections of particles with a charge and keeps moving on in the circle, or recession, rotation, also vibration. Not only that, these two lines come close and swing in and out, like bending vibration, not just stretching vibration. All of them, they have different frequency. So using different frequency photon, we can interact with those vibrational modes because they have also harmonic function. Therefore, we eventually can compare that input and the output after interaction. We can specifically say we have a such bond type, such atom nuclei, or such electron in such a potential energy level, and so on.